Hmm. I think that you're right that you cannot have a monad morphism from a monad to a smaller monad in some sense. So a monad morphism from some monad must be to a larger monad,
Right.
which is large enough to describe the effects. Although sometimes you can discard some information, but not always. So you can have, for example, from either into option, you can do.
Yeah. Right.
So
if you're willing to lose some information, that's a possibility,
right,
but you still have to handle all the cases.
Yes, right.
So you can't really like go into the identity monad from sum, you know.
So
yeah, I get your point that, you know, if you have a super monad like IO, that you can basically do everything in it, but maybe inconveniently, then maybe you can keep your original monads and then have monad transformers into the super monad in order to actually do the work.
Well, not the transformer, the monad morphism. So
morphism,
right?
Yes.
So we have this. So the coproduct construction requires you to have monad morphisms into some target monad. So if the target monad is IO, then I argue you always have those morphisms. So if the target monad is identity, then you don't have, in most cases, you cannot have those morphisms. And the coproduct construction actually requires those morphisms. So if you don't have those monad morphisms, or if you just have natural transformations but not monad morphisms, then what happens is that the result is not not a well-behaved monad transformer. So it does not have the properties that you want. So then if you do that, things can depend on many things. So you can there might be a refactoring of your program that fails because of violations of monad morphism laws. And there might, so anyway, this is, it is no longer the coproduct. It is actually a different monad, which looks like it's a coproduct on the surface, but it isn't. So you see, we have this, you have the quantifier for all x, like rx to mx or whatever, but that does not fix the monad morphism properties of that function. So that quantifier,
which are like that ID goes through and it's associative or whatever.
Well, the multiplication of the monad is mapped into multiplication of the other monad, and the identity, the unit of the monad is mapped into the unit of the other monad. So if you don't have this, if you just have say a natural transformation between Rx and Mx as functors, then on the surface, you know, in a language like Haskell and Scala, you won't notice because you're still passing those functions. The type signature is the same. The type signature does not include monad morphism properties.
Right.
And so your compiler won't notice and you won't notice, actually. You know, if you put in something that you believe is a monad morphism, but you're mistaken, nobody would notice. And so so the result is that you have constructed a monad which is not the coproduct, so it does not have the properties guaranteed by the coproduct. And so if you're relying on those properties in any way, then you might be mistaken. And
well, maybe in a dependent language you could express those properties. Absolutely. And then, you know,
absolutely, yes.
Then you would have a chance of knowing.
Because in a dependent language, you actually should be doing that. You should be having your completely lawful type classes. And I mean, the instances for laws are not more complicated to fill in. So there's no excuse if you have a dependent language, there's no excuse for not including all the algebraic laws. They're very easy to express and very, very easy to satisfy for all the instances. And so in my book, I have a lot of those constructions that show, like, if you have two monads, and then the product of the functors is again a monad, and the laws are still holding. So you can construct the proof that the product of two monads satisfies the laws from the proofs for the smaller monads. So, and this is the case for all constructions. So essentially, you could just follow the types and construct mechanically all the required proof terms for the laws. So there's no excuse for not using them. So,
what about like the what do they call it? The mediating morphism. So, really in the coproduct, you're going from whatever your plus is to your monad M, or they called it S. And that is more than a natural transformation. That's also a monad morphism. Yes. So in theory, you would have to then prove, the laws for that.
Yes, but this is guaranteed.
Saying it's straightforward.
Well, if you need to have a specific type for your coproduct. So for example, this type that I was writing, you can just prove that. You can just prove that the laws hold. And there's no it's straightforward. This type is essentially a church encoding.
Right.
And it's very easy to get all the proofs. So what I'm saying is that coming up with proof terms for laws does not require ingenuity. It does not require you to kind of think. It's just mechanical. So for all constructions, for all type classes, it's just a mechanical activity. So it could be put into a library.
Or maybe there's some base monad morphism class or something. Or I don't know exactly.
Okay, well. So, all right, so shall we begin?
Yeah.
Hello, Yamil. So we have a small group.
Antonio.
small group today.
Yeah.
Hugh is not here, and somebody else wanted to come and he couldn't come. Okay.
Right. Yeah.
So should someone? I might need to drop off at some point as usual, but hopefully not for very long. If my daughter needs me to go to bed, but anyway. So would someone want to share? See the screen.
I mean, I could share, but I didn't get I got lost pretty quickly.
Oh, okay.
Okay.
Mm.
You could see that.
Yeah.
Is that okay?
Yeah, good. Thank you.
Yeah, representing the Yoneda lemma using an and I'm curious. I'm trying to intuit what that means. I still am not quite comfortable with the definition of an and, so I'm still struggling at that point.
Let's see, where is that?
That's page section 2.1, the Yoneda lemma. I mean, the intuition of representing a complicated type using a simpler type. I mean, I think that's the first example that they give on section 1.1. I thought, wow, that's very interesting, right? Because
yeah,
there's
you're going from this
to this,
to this.
yes.
That's right.
So it makes me think, then why do we even need the type on the left-hand side if it's equivalent to the type A cross B arrow C? It seems like, what happened to the functor? What's the intuition here then? Instead of this kind of a universal, for all F's, this type, we can just use the A cross B arrow C.
Mm-hmm.
And then, so why do we need the left-hand side?
Well, what do you mean you need? You have a type on the left-hand side. Maybe you had to work with some types with quantifier for any functor. And then after some work, you have simplified into this form.
Mm-hmm.
And now you say, oh, but I can get rid of the quantifier now.
Yeah.
So
because the essence of that type on the left is captured by A cross B arrow C. You just need an element of A, and then you just need a function from B to C. So
right, so you can use your functor to get a B and then transform it to
but you see, so this is a type equivalence. So
yes,
you can have code that just produces a function on the left if you have a value on the right.
Right.
Or
which
vice
is
versa.
Pretty much this code.
Right, yes. So yeah, so I mean this is so I can tell you why I was interested in this paper. So there are two reasons. First reason, this, like what Yumila was just saying, there's this spectacular simplification where you have for all functors something, which is complicated, and that is equivalent to a type that has no quantifiers and much easier to work with, right? So imagine this could be would be a very useful technique for reasoning, right? And this doesn't just work for functors, this works for everything, for any type class, like monad, applicative, they give an example, right? So for all applicative, for all monad, and obviously this is not limited to applicatives and monads, it's just for a very large class of things that you can do that. So this was the first thing. So how can this be? How can we understand this spectacular simplification? And second, at the end of this paper, they prove that all traversable functors are polynomial or something like this, not finitary or whatever that is. Which is another very interesting thing because it's not easy to prove that kind of thing. Traversable functors are difficult to work with because they don't have laws that fully characterize them. In some sense, they don't have enough laws. And people who are struggling to find adequate set of laws for them. So just to remind briefly, the traversable functor means that you have a data structure such that you can traverse it, iterate over its stored data, applying some transformation, but this transformation is effectful. So it's not just a function, it's a function into a different type, it's a function into an applicative functor. And so then all the applicative effects can be merged as you go. So you traverse and you merge the first item, you generated some effect. Then you go to the second item, you merge with the first effect. You generate the third item, you have a third effect. You merge again. So you merge. So you have a big effect at the end with all the items already processed, but they remain in the same structure. So this is a very interesting transformation, which has a lot of applications in practice for compiler writing, for example. They invented it for compiler writing. And I used it when implementing some type checking and something for the DOL language, where you can just your code becomes very short once you do the traverse. It's just everything works. The tree-like structure, and you type check the tree-like structure. You type check recursively, and type checking is effectful. It could fail. Right? It produces a type if the types are valid, but sometimes it fails, and then it's an effect. So all of that is automatically accumulated. And you have you have typing context gamma, which needs to be passed through to the sub-expressions. All of this is automatic. So you see, because you just put this into a big applicative effect and you're done. It's amazing. The code becomes so short, you don't pass through all of these things laboriously. Everything is automatic. Anyway, so, but traversable functors are hard to work with. It's a complicated type class, and in particular, there aren't enough laws that can be formulated to say, well, this is a lawful traversable functor, and this is not a lawful traversable functor. So anything that you can say about all traversable functors, so here they claim that they prove that all traversable functors must be container like functors, and that means essentially you can write down what it is. In general, you can formulate what is the property of being traversable, and what are the traversable functors. So then this is, to me, this is also very, very interesting. So how can you do that, and why does this? Why is it related to this representation theorem? A to FB TA, because apparently it is, because it's of this form, A to FB to FC, where F is an arbitrary applicative functor. So look at just what's on the screen right now. Traverse FAB, right?
This guy,
right? Now this has a quantifier of F in front, where F is an arbitrary applicative functor. They don't write it in this line, but this is what it must be. So, this has the same form as this type in the beginning. A to FB. Well, TA is just a constant. You can pull it out, right? So this has this form: A to FB, parenthesis, to FC. Now, T is fixed. A, B are fixed types. So TB can be just read as a fixed type in this type, right? So
well, we're characterizing T, right?
Yes, we're characterizing a fixed type type constructor T, but F is under a quantifier.
Okay.
In this formula, they should have written it down more clearly. So this is in the same form. So then they can apply this theorem, because you have a type of this form, A to FB to FC, and this needs to work for all F, and F needs to be applicative. So it's interesting that somehow they apply that theorem, not to, well, you can say, I want to simplify the type of traverse into another type, which doesn't have the quantifier for all F.
And did they do that?
I don't know. This I actually never understood. But that's what they should have done. Is that, okay, for every traverse, there is a corresponding co-algebra, blah, 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 blah. So anyway, this is my motivation. So, and also, I have actually used this theorem to prove interesting results about monads. So A to F, B to FC, right? So this thing, where F is an arbitrary monad. So for all monad F, A to F, B to FC, and again, they have a right hand side, which is not the same as for functors. So maybe you can go back actually to the formulation of the section 3. What is the, yes, so what is the formulation of their theorem? So there's this R,
Where are we?
So, for example, let RAB, and so this R is a very important
Oh, this
factor.
guy, yeah.
Yeah, which is just fixed functor, on which we will then do the free construction. The free functor will be applied to R to generate what they call R star. So then they calculate A to F, B to Fx. So, okay, right now, then we calculate. Can you scroll a little up to the beginning?
Okay.
Yes, that's right. Yeah, that's it. So these are the three lines that they want. And
oh, I see. And so here's the final
right
thing,
so,
and this left-hand side is equivalent to that for all that we saw.
Right. That's right.
Right.
Yeah.
Well, it's this next line.
Right. So there is just a few lines actually. They're not so difficult to follow. The proof is actually not difficult. It has about 4 steps for the more interesting case, which is the next 3.1. But anyway, so first we have A to FB to Fx. Then we say A to FB is the same as RAB to F. That should be a star, actually. But anyway,
which one?
This one. So
that should be R star.
No. Well, for the functor, no. For the functor, it doesn't have to be. But the thing is, a morphism from A to FB is adjoint to another morphism, which is RAB to F. And that's what they have to do. And then this is UNIDA. Then this is UNIDA in the category of functors.
So this equation is using the adjointness of these things, right?
Yes,
and then this is UNIDA.
And that is UNIDA in the category of functors. So for all F, something to Fx is that something x. So this is, so at each stage, yeah, that's what it is. Now, that seems to be very, very interesting. But if maybe you can scroll down and see what happens in the more general case. Yeah, okay, 3.4 is very important. So then you have this E star to F is equivalent to E to UF, right? So this is the adjoint injunction, the equivalence of morphisms.
Are we assuming that these guys are adjoint, I guess?
Well, you construct the adjoint because there's an adjoint of forgetful and free. You always have that. So there is a forgetful functor, which is U, and the adjoint, which they call the star, which is the free functor. So the free functor is this
guy.
F. Yeah, so F star would be.
Yeah.
So E star is the free type class generated by E. And then from that to F is the same as from E to UF. And this is from a programmer's perspective, this has a very easy interpretation. So UF is just F. In the programmer's terms, the forgetful functor doesn't do anything. The data structure doesn't change. So
because you don't have all this extra stuff.
That's right. You don't have the laws that the dependent language would impose on your.
You don't have the operations either.
You don't have the operation. Well, they aren't in the type. The operations aren't. The type is just a type constructor. So the operations are somewhere else. and
right.
you don't see them. And so on the right of 3, 4 is just a natural transformation from E to F in the programmer's terms, which means I need to run E into F. On the left, it is a free structure on E run into F. And for a programmer, this is clear. If I know how to run E into F, how to interpret E in terms of F, then I can interpret the free structure on E also. So for example, if I have a functor and I know how to map that functor into some monad, then a free monad on that functor is also mapped into that monad. All the monad operations are mapped by freeness, and the core I know how to map. So, or free monoid, it's the same thing, right? So if you have a free monoid on a type, a type itself is not a monoid, say, but free monoid, excuse me, free monoid on T is just a list of T. And if you can map T into a real monoid, you can also map list of T into that monoid. It's very easy, right? So if you can map T into a monoid, let me maybe write it down. It's easier this way. So if you know how to map T into M, and M is a monoid, then you can map list of T into M as well, right? So
by mapping each T into M, and then
and then
each element of the list, and then use the multiplication of M.
That's right. So if the list is empty, then you have the empty element of the monoid M. And if the list is not empty, then you just multiply all of them in that order. So this is a simple example of the same thing. So if you have T of M, then you have list of T of M. And vice versa. If you have list of T of M, which is a monoid morphism, then it's equivalent to having just T to M. And so this is 3.4. This is the equation 3.4. So these two are equivalent. So functions T to M are equivalent to monoid morphisms.
Okay.
Of list T to M. So this is a really for a programmer, it is clear. You know, I can obviously map that free structure into some target structure if I know how to map the thing from which it was generated. That's sufficient. So that is a key part of the proof, actually.
So can you interpret 3.5 for us?
Right. So 3.5 is what we want to prove. So what do we want to prove is that for all, wait, where's my pencil? Where's my pencil? So for all F, say monad, A to FB to FC, right, is equivalent. So this is the left-hand side of 3.5. So okay, so this was 3.5.
Why C instead of, is CX there?
Yeah. Let me write X instead of C.
And you're just throwing away the U because
I'm throwing away the U
because from a
programmer's
point of view, it doesn't do anything.
Right, it doesn't exist. Right. I mean, we are writing in a non-dependently typed language, so we don't see this U. Okay, so IE to FB to FX, and then I have a free monad of this R, applied to X. So you see, so the R is always the same for all of these constructions. R is this thing, which is Rx equals A times B to X.
This thing.
Yes, it's always the same for all type classes. So it's the same for functor, for monad, for applicative. But so here I chose a monad, and then therefore I need R star on the right hand side of 3.5, and R star is the free monad on R, which is a free monad generated by the functor R, which means that I can write it down quite quickly. So what is a free monad on R? It is, let's call it F, no, not F. What should we call it? Let's call it T. No, let's call it G, okay? So what is G? So Gx equals X plus R Gx. So this is a recursively defined, so G is a recursively defined functor that looks like a tree with leaves of type X and branches described by R. Right, so a simple example is when R A equals A times A, then G will be just a binary tree. Gx is X plus Gx times Gx. So it's just a binary tree with leaves of type X. But our R is not A times A. Our R is this complicated thing, A times B to X. So this is not really so easy to interpret in terms of a tree. But anyway, this is the free monad construction.
Okay.
Which is a recursive type, but it doesn't have any quantifiers. So it's certainly much easier to work with than this original thing, which is for all monad and then blah, blah, blah. Right. Yeah. So anyway.
It is kind of amazing that the monad of the left just disappears.
Yeah, it's just totally, yeah.
Quantifying over it, I guess, you get to use it whatever way you want.
So I can expand this and I can just define G like this. So Gx is X plus A times B to Gx. So this is a recursive type, Gx, that I just defined. And that's the right-hand side of 3.5. So on the left-hand side, there is no recursion. There is just a big quantifier over all monads, which is a difficult thing to reason about. On the right-hand side, there are no quantifiers over monads, but there is a recursive type.
And so G superscript R is basically using R to F map G, right?
Where do you see G superscript R? No.
This right around here.
No, that R belongs to the previous line.
Oh, never mind.
Yeah, I'm sorry. I should have.
That R is subscript of free monad.
Sorry. Yeah.
No. Sorry. This is confusing. Yeah. No. So there is no G superscript R. So G is just a type constructor. So G is a recursively defined type constructor, which is like this. And certainly it's not easy to work with, but it's much easier to work with than this huge quantifier over all monads.
Oops.
I can delete this because it's anyway.
Okay, it's okay. I'll try and get it where it looks.
Let me just clear this, and so okay, right. So yeah. So this is quite amazing. That so the proof is actually very short, just 4 lines. Right. So first we have this A to U of B is the same as R AB to UF, which is just the definition of R. Right. So what is R AB to UF? That is for all
Well,
X.
actually, equation 2.2 is proposition 2.2. So that's a little bit application of Yoneda and some other things, but
right.
Okay, yeah.
It's like this. Right. So A we can carry over. Right. So let me just write it down. So A curry B to X to Fx. Now that is Yoneda.
So just to back up a little bit, they're using equation 2.2 on this part, right?
Exactly.
To turn that into this.
Yes. So I'm showing why that is true. That's just a Yoneda lemma and the specific definition of what R is. So R is this A times B to X, and then A you can uncurry. You can curry A, and then you have A to FB because of Yoneda. Because you have here B to X to Fx, that's FB. So this is a programmer's way of showing that this is the 2.2 works. I mean, there are. So then we have the next line, which is RAB to UF, and that's the joint to R star AB to F. So this is again, this is the step.
So we're working on this inside part again.
Right.
It's not working, but yeah.
Yeah. So right.
And that's a jointness.
Okay. Yeah. So that's a jointness. So the morphism on the previous line are into one correspondence with morphisms in the next line. And then finally, you have just Yoneda in the category of F type class. So whatever that is, it's just Yoneda. And that, I mean, every step here can be written down as code in an ordinary programming language. So if you have, functions of type given by the first line and the recursive type given on the last line, and you can write code that transforms one to the other and back. It works. You just have to ignore the U. You have to substitute what the star is, and then it just all works step by step. So I went through this because I had to translate. So what I had done is I said, so let's say this is F is a monad, so we are talking about all monads, and I want to find the following for all A, M, A. Sorry, no, that was not right. For all A, A to MA. Right. So I want to say, well, if I have a function which is a type signature of return, right? But this function needs to work for all monads. So does it have to be a return? And you can prove that it has to be returned. So this is actually is isomorphic to the unit type. There's only one function that has this type signature and works for all monads. This is not a very deep statement. And then I had also a deeper, more complicated statement.
But you're able to make that isomorphism by using this kind of stuff.
Yes.
Okay.
Because I can just massage the types and use this theorem essentially.
Okay.
I can eliminate this horrible quantifier, which I don't know how to work with. Otherwise, nobody knows how to work with it. For all A, MA to MA, and this needs to be a monad morphism. So, and that is also equivalent to unit. So there's only one monad morphism that works for all monads, which is this is identity. So this is a statement that I wanted to have for a long time, the last one, from my book. Anyway, so these are applications, so to speak, of this theorem. So you can, I don't want to go through the proofs, but essentially you can eliminate this quantifier, this horrible for all monad quantifier. The price is that you are now working with this. Okay, well, this is a recursive type, which you have to work with, but there are no quantifiers in it, so you can work with it. So you can. It's easier to reason about that. This is just a specific type, right? So there are no quantifiers in it. There are no for all monads. There's no, So this quantifier is very hard to work with. So anyway, that's this is actually a very deep result, I think.
So your your co-product type had a for all monad,
right.
all F monad in it, or M, whatever. Could that be simplified using this?
Right. So how did that go for all X? P,
like left of X or whatever.
X to MX for all X. QX to MX. For all what? And then what? I forgot what
it's like for all X, M of X.
MA. Well, it's a different, there must be a different type parameter, but where does it come from?
Yeah, well, you had, I think, the for all A in front of or lambda A in front of the for all M, but
right, lambda A, right.
You could also think of it as that the end is being sort of for all X or for all A, M.
No, it's not a for all A, it's a lambda A, you're right. Okay. That's good. Yeah, that's good. No, it's certainly not a for all A. Right. So this is a type constructor, so it has a capital lambda in front.
Okay.
Right. So okay. Well, capital lambda we don't care about that. We just forget it. A can be a fixed type. Okay. So is this of this form? there are quantifiers inside, so this it doesn't look like it's of this form.
Yeah, I mean, you could join. Yeah.
Sometimes you can get rid of
cross
them,
product the two for alls, but that does. But then
no.
getting inside those for alls is hard. So.
Right. No, I don't see that this. And also another thing is that these are monad morphisms. Whereas in this theorem there are no such restrictions, because you see there's this u in here. So this arrow, this morphism, is not monad morphism. It is just an ordinary morphism because you have the u. So u erases the requirement of having monad morphisms. And so, yeah, no, I don't see that this can be done.
Okay.
I don't see how we can do this. But anyway,
yeah.
Okay, cool. That's about as much as I can say. But I just want to say that I was able to go through this proof step by step. You know, go back to 2.2. What is the code that they showed in 2.2? Go back to 3.4, right? So 2.2. Now let me get rid of this. Right. So 2.2, right? So they have the right code, following functions, alpha, right? So you have these functions. Okay, so they give this code, and then 3.4 is again specific code that you can write down, and so on. And I was able to just piece this together and have code that transforms the initial into the final type back. And yeah, so this was not so bad, I must say. So I thought it was some kind of very, very mysterious theorem, but actually each step is not mysterious. So each step is just code that you can write.
When I looked at this before, it seemed like this composition was in the wrong order. Because, well, I don't know. I'd have to
RAB
go back.
X RFGH.
Right, because these F, G, and H are morphisms in set up, and set, right?
Yeah.
And
let me see. FGH. So what is H?
H is like the X
from X to Y.
X to like, yeah, X to X prime or
X
something
to X
like
prime,
that.
right? X to X prime, okay. And then
we're trying to come up with something.
What is lowercase x? Oh yeah, it's a function. Okay, lowercase x is a function from b to x, right? Lowercase x is a function from capital B to capital X. And H.
Yeah, it would be.
And G.
Right.
This is really weird. Yeah, it's a model. You're right. I think that's right.
Because you're trying to produce one of these, that like the primed version. And so you get an A, and the X is kind of like this guy.
X is that guy, right?
Right. And so
H,
then
H is from, so H is from X to X prime. And G is from B prime to B. something like that, right?
And F is like A to A prime or something.
And what we need,
well, that we don't need that here. Okay,
is B prime to X prime. Have is lowercase x, which is B to X, right? So we need to get B prime to X prime, and we have B to X. So what do? Well, we take a given value of type B prime, we apply G to it.
Right.
The result is a B, we apply X to that. The result is an X, we apply H to that. So actually
which makes an H prime.
G
X prime.
X H, or H X G. The first thing to apply is G.
Yeah. Okay, good. I wasn't crazy.
Yeah. No. This is one of those cases where they write it down, but they never use this.
Mm-hmm.
Right. They never lift any functions to the functor R. So yeah, it's wrong, but this doesn't affect anything.
They're not using R functorially,
no,
I guess.
No. Well, they don't need this formula. They don't need the code for the for this mapping. This is never used. Right. So, so for example, when I was deriving this MA to MA, right? So for all monad M, MA to MA, I was able to write down code that transforms this difficult type into a simpler type. It was not extremely simple, but I was able to transform step by step, and then the result is I can write it. Maybe it's a little interesting. So for all M monad, for all A, MA to MA, right? So I can prove that any function of that type must be f of M must be of this kind. So you must have a certain number of copies of M. All the effects are evaluated, but only one of the values is chosen. One of the values X is chosen, all the other values are ignored, and then this X is returned. So I was able to prove that all the functions are of this form. I have to go attend to my daughter right now, but I'll be back hopefully.
Okay. Trying to find it. It seemed like they had like if you have a functor with more structure, the law is simpler, but I don't know where it is now. Okay, so this is sort of their unary representation, and then I guess they handle the case where you've got like a more general thing with a lot of these different types in it, and then they come up with a similar kind of thing with a big product on the left, but also the for all f, a product going into this, and then you get basically the forgetful on some sum, but using R, and then that whole thing turned into a free monad. No, I guess that's what you have if you have this more general structure.
Hmm.
So I don't know what this is about.
Lens part,
What's that?
the part with
The
the
lens
lens.
part?
Yeah. I'm wondering what the difference is between a very well-behaved lens and just a plain old well-behaved lens. But
Huh.
but I wasn't curious enough to look it up.
Yeah. Okay.
Well, even more basic is what's a well-behaved lens as opposed to just a lens?
Another good question.
Is
I
that
would assume,
common? Is that common terminology so they don't even need to explain it in this paper?
well, I've never
I think they have this, well, it wasn't there, but they have a reference. Actually, you could go look it up, I guess.
mhm.
Yeah, okay.
Right, I've never seen the distinction between well-behaved and not well-behaved, or very well-behaved and regular well-behaved, in any discussion of lenses I've ever read.
Mm-hmm.
Introduction, they said that they eventually say something about like effects, but I don't know. I don't know where that is. Yeah. Okay. Thought in here somewhere they said, okay, if you just have like a pointed functor, then the law is simpler, but it didn't look simpler to me. Let me just see something. So if your functor is pointed, then instead of just getting A cross B to C, you get A cross B to C plus C. And they say that's simpler, but I'm not quite sure why. But I guess the thing is you can, you need this in order to map the point, I guess. And yeah. And a simpler type represent seems to be that. And then they give the isomorphism for doing that. And it's like if it's going in this direction from right to left, if it's the regular part, you kind of do what you did up there. And if it's the right hand thing, then you use the eta to inject it into FC or into this thing. Something like that. Okay, anybody else have anything to say about this?
I guess not.
Yeah, I kind of found that the writing was pretty good. They kind of would stop and explain things, but it's also very dense. You know, it's like, well,
Right.
show you this, and you know, here's some code. You know, here's the code. You know, that sort of does it, but like actually parsing out that code and figuring out how it works is, you know, it's tricky. You know, it's like,
Yes.
they're saying there's enough information here to understand what they're talking about, but you have to think about it in order to really get it. So it's, yeah, fairly dense. So, do we know what we're going to do next time?
Let's see. Did Sergey have another paper that he was suggesting? Was this the last one in our queue?
I don't know what's the cue. Today, Sergey commented on sort of, I guess, a Scala library, KYO, that seems to be a super effect, like monad, kind of like effect combinator kind of thing.
Right.
I don't know if we want to look at that, or it's probably Scala specific, but
I would expect it would be. Novel approach based on algebraic effects. Joe achieves this without inundating developers with concepts from category theory. How refreshing. I guess this would not be a bad thing to.
Oops.
It might at least give us some fresh ideas about syntax for effects and effect handlers.
Okay.
Right, so there's, right, the introduction seems to be rather long and detailed and full of code, and I don't see any category theory anywhere. So yeah, that
where this
would be a fun break. So if you're looking at the Slack, Sergey's post of 9:04 a.m., he mentions the framework get /ID equals getting started. That link does seem to take you to a user manual of sorts.
Yeah. What happened to my Zoom window? Oh, there it is. Yeah. That's that one. Okay, I guess that's what it points to.
I'm just reading some of his comments from earlier today about how IO monad is this anything can be
Supermonad.
mapped. Yeah, anything can be mapped into IO, and I guess that's true because basically IO is like representing the whole world. So
Right, it's a big rug under which you can sweep all your effects. Right.
yes, that's why most programming languages are just IO, right?
They
Yes.
just use IO.
I mean,
Yeah.
a C program is you write it inside, you're writing inside on IO. That's it. I mean, a Haskell program, if you write everything inside a single IO, then that's it. That's a sequential code that you're writing. So yes. So IO definitely does have that feel, but which is why you want to restrict and not live inside IO all the time.
Yes.
But this Q is kind of it's fascinating that Scala has this dual people writing Scala code. Either they are writing Java or else they're writing Haskell.
Yes.
So, and the two are kind of, they don't understand each other, or at least the Java people do not understand how the Haskell types want to write everything. So,
right, but it provides an entry for people from either world into the other.
yes, except it's kind of bimodal, I think, the way the code is written. You either pick the class-oriented approach like Java, except with a terse syntax, or else you start writing these complicated type signatures, which
Yes,
don't, yeah.
Once you've signed on to the functional style, it is yeah, all of those complicated type signatures are difficult to discard, I guess, in order
Yes, exactly. It's inevitable. It's inevitable, right? Yeah. Once you try to do it functionally, then the types start getting more and more complicated.
Yes, but the code gets reusable.
Right.
Whereas if you just program in the direct style, your code is not terribly reusable. And
right.
you can implement the effects in that you're referring to in the functional style with code in the direct style.
Yeah.
So he keeps mentioning Cat's effect. I think, isn't Cat's like a Scala library that's sort of
Yes, I believe so.
on top, almost like at the meta level or something, or maybe it's a different one, but yeah.
Well, it's a
special one.
category-inspired library of functional stuff.
Right.
So, I don't know anything more about that. I've seen examples of it. But,
Yeah, I think originally CATS was like, you know, category theoretic things in Scala, but then they added effects, which is now the you know, because that wasn't sufficient, they now have more that is effect driven, I think, to try to encapsulate effects. So I think CATS dash effect is a subset of the whole library.
But is it what people generally use for effects now in Scala?
I guess so. I think ZIO is the other one that some people do not like because it's too. It's kind of like the difficulty of a huge monad, right? Basically, ZIO says let's encapsulate everything into a single monad.
Okay, kind of like what Sergey was talking about before.
Yes, exactly. And so you look at ZIO and it's like, oh, I have environment, I have this, I have that, I have this, I have error. Let's just put it all into one monad, and then you can use anything, right? So yeah. And the guy, what's his name? Oh, I all of a sudden blank out. The creator of ZIO, John DeGoes, I think has been sort of a controversial figure in Scala. So because of his approach to that.
You mean like some people don't like the ZIO approach? Or?
Exactly. Yeah. Because it tries to, I don't know, encompass everything into a single monad, and then obviously you can do everything, but then there's a certain amount of complexity, loss of elegance because of that. And then recently his company, he said that he has moved away from Scala and is now doing Rust or some development. So yeah.
Yeah,
The politics.
Yes. Find a nice abstract field like programming languages that should be completely free of politics and discover that it is actually full of politics.
Yeah. I mean, Rust definitely has, the creator of Rust or the group that created Rust, they definitely appreciate the type systems of Haskell and the like. So you can see that in the type system that Rust has. So they definitely come from that orientation.
Yes.
Yeah.
But they also seem to have like a C++ orientation, sort of.
Not as much, no, because it's not an object-oriented programming language.
Rust isn't?
No, Rust is not. It's kind of like Scala's traits, right? You have traits, but they're not classes, right? So if you take the class away from Scala, then the remaining things like traits allow you to define the signature for an algebra and things like that. And then you can implement traits and so on. But there is no notion of inheritance. Um, so,
but don't they have like basically objects that hold data at least, and then
yes,
you can
you have containers,
mutate them or whatever in a carefully controlled way.
Yes, that is true.
And so in that sense, you're mutating state in that an encapsulated state. So in that sense, it's a object, I guess, is what I would think.
Right, but the methods are not associated with a particular object, like as in class. Hello.
Hi.
Hello.
We're sort of supposed to be talking about the paper on representation, but we kind of have veered
Sergey
into
left
some general.
We don't know what to say.
Yeah.
Right. Nobody understands enough about the paper to say more except Sergey, and Sergey stepped away. So so now we're talking about what we might do next time. And Sergey in the Slack posted something about Kyo, which is this effects framework, which looks kind of interesting because it touches on some stuff that we did previously in this track as well as in the other track. And so
is that framework a Scala framework?
It is a Scala framework.
Yes.
Right, okay. Just making sure I'm keeping the track. This track is the one that primarily a Scala.
Yes, well, it's
because Sergey's book is Scala.
Yeah,
yes,
Sergey's
yeah,
that's true.
It was a lot about Sergey's book recently. Yeah.
Yeah. Originally, it's supposed to be, I guess, a category theory track, but it's also also about more specifically the theory of programming language structures.
That reminds me, you guys may be interested in this. I saw an announcement on Reddit that a new functional programming book was out, and I believe that the main ideas are all shown in Haskell, but the author was saying that the way he covered the material should be applicable to Scala as well as some of the other like more mainstream functional programming like F# and OCaml and stuff. I think OCaml might have been the weakest one in terms of like how well he understood whether or not the concepts would be portable. I'll find the link real quick.
Right. Well, vanilla Haskell is very portable. It doesn't really use ideas that are, I mean, it uses very basic ideas that are common in many programming languages. So
You're saying vanilla Haskell is?
yes. Well, I mean, once you start turning on the infinite numbers of switches, who knows what you get.
If this ends up being interesting, I could post it to the Slack instead for posterity, because I know this stuff just goes right into the ether when we disconnect. But there's the Reddit link. And the reason that I thought of it was when you said category theory. It's just that in the links that this guy provides to other books, and he's of course plugging his own book, but he talks about some of the other books that were already in the field that were written by people that gave him nice reviews or some sort of they said nice things about this book that he had just finished. But one of the other things he cites is this thing called the voids of Haskell, which I think is basically, he's basically saying these are the missing books. Like if Haskell had a better collection of books, then there would be things on these topics. But I thought I remember seeing in the links in this somewhere a link to category theory stuff that I knew about the person, because somebody had told me about their YouTube videos, but there was like a website to go with it, and I did not realize that there was anything but the YouTube videos. And I can't remember the name of the guy. It's like Bartoski or something like that.
Is that Milosevic?
No, I can't find it with BAR. It's gotta be in here somewhere. No, it's not BAR. Maybe if I just search for category.
Milevsky. Bartosz Milevsky.
Yes, it's just that his name is not called out in that page. So in the Voids of Haskell link that is linked from that Reddit post, there is a link to this. And I didn't realize that he had prose to go with it. I knew about the YouTube series that he had done, and somebody highly recommended it. And I watched the first episode of it, and I was like, wow, that actually is like, it seemed very approachable. So, like, I mean, if I understand it correctly, he's basically like a mathematician, and so he is explaining it in those terms in his videos, but to the degree that category theory is like always made into be this like really complex topic, I feel like the way he started breaking it down at the beginning, it just seemed really approachable.
Yeah, so a few years ago, we actually went through Milevsky's category theory videos.
Okay.
And yes, the first few are really quite oriented towards programmers and are fairly straightforward. And then they start to get a little more abstract and a little more category theoretical. And by the end, it really doesn't have much to do with programming at all.
Okay, that's funny. But yeah, so I saw that link in this Voids of Haskell, and I was like, oh, he's got because it really looks like it's basically a book.
Which one, Milevsky's? Or this
one? that second link in the chat that I put.
Oh, where'd it go?
Talks about like it's a table of contents. Category theory for programmers, the preface.
Yeah. Right. It's kind of a big blog, but
right. Functional design and architecture. So this says the ebook will be available starting October 15th, 2024. So it is.
Okay. Oh, yeah, I see that now. Yeah.
Mm-hmm.
Okay, so that's why I hadn't previously heard of it. Perhaps this is that I didn't know he had a blog. But I guess the good news is that he's going to roll all this up into a book.
Right, but this is not Milevsky. This is what is the author's name? Granin. Alexander.
Oh, it's not actually his book.
Right.
Okay. Well, excuse me. I have not had any coffee yet today, and I misinterpreted what I had seen in that. Well, I just bookmarked that Reddit post for later because I was like, oh, there looks like there's some nuggets of stuff in there. Just the Voids of Haskell, that page seemed to be touching on a bunch of different interesting topics. And
right. Well, that doesn't mean the book isn't interesting. So
Yeah. So anyways, that book, that Haskell book is out. This other book is coming out. But none of those are anything to do with Scala per se. The Manning title that just got released, he did specifically say that it should be approachable with Scala as well. But I don't know if he actually said that he wrote any Scala code in his Git repo. I think his example code is Haskell.
But yeah, I mean, you can always leave the translation to Scala as an exercise for the reader.
Yes. If you know enough Haskell to translate it into Scala, then you don't need to translate it into Scala.
Well, unless you, for some reason, need to use it in Scala, yeah.
Right. But you already have to know Haskell.
Yes.
But yeah.
Do you guys feel like Scala is an acceptable alternative to Haskell when you need to target the JVM? Like, does it qualify for that lofty of a?
Well, I haven't heard of any Haskell compiler that compiles to the JVM. So,
well, there is Frege. It's old news, unfortunately. I stumbled on it recently, but it doesn't look like it's really being maintained anymore. But it does target the JVM. And it's not Haskell proper. I think that there were some things that got tweaked a little bit, but it's really trying to be Haskell as much as possible and still target the JVM. And it is open source, so it's it could be could be revived at some point by somebody. I don't think the guy that started it is working on it though.
I think just targeting the JVM maybe is only half of it. I mean, the part of what made Scala so popular was that it could use basically the Java libraries. You just could, basically include them, in a various ways, and then, and then use them in Scala. And furthermore, Scala gave you some like additional features, like you could make some of the classes more easy to use and stuff like that. So, but sort of my point is, it's like just targeting the JVM may not give you the advantage of using all the Java libraries, just sort of the way Scala does.
Yeah, I think that's a good point. I don't know what the interop story was for Frege.
The most straightforward thing to do would be to just, the basic language constructs ought to translate easily into Scala, but the library would be, the libraries would be much more of an issue. Anyway, Sergey is back.
Yeah.
So we were discussing what to do for next time. One thing we could do is we could look at this framework Kyo that you posted about. Is that something we would be interested in looking at for 2 weeks from today?
So what's the plan about it? It's a relatively new open source framework that is Scala 3 only, as far as I understand. And it's I think it is more in the spirit of effects and handlers, like plain effects and handlers.
Right, that is what it looks like. So we could try to read the intro to it and see if we can figure out how it maps into stuff that we understand.
Yeah. That's,
Were there other things, Sergey, that you had suggested in the past that maybe we would look at? I was trying to remember.
Nothing comes to my mind at the moment as to what I might have suggested in the past. I mean, this the Kyo framework fits more into what we were discussing, right? The effects and handlers stuff. We might try to write some code with it and to see what happens with states either and so on. If you choose, if you're just trying to poke at it and see what happens with effects and how that runs, because to me, I posted in the channel a link to the discussion that the author of this recently posted. It looks like he's talking about these values, right? So there's this value with effect, right? So he talks about them as if they're just deferred. So you have a value 15, but you can't look at it because it comes burdened with all those effects that you have to handle first. Right? So it's 15 with abort, with state, with I don't know what else, and then so once you handle those effects, and you get the 15 back.
Right. So you have some sort of computation that returns 15, but it's an effectful computation, and something happened along the way.
And you have to provide handlers for all those effects. And once you provide them, then you might get your 15 back, or maybe not. And so, in some sense, 15 is just deferred. So it's deferred until you handle all the effects. And so, in this sense, it doesn't matter what those effects are, and you just need to handle them. So so you can introduce any number of them. It's kind of a more general effect system. So if you come up with some type, it's whatever signature that needs to be, then it's your new effect. So you can create arbitrary new effects and handle them in arbitrary ways. And you can have whatever concurrency as an effect, or states manipulation, mutability as an effect, or something else as an effect. So linear. I don't know.
This linear, is all. This is in KYO.
Yes.
Yeah. Okay.
So apparently you are able to do this, and then you somehow, the framework provides a lot of effects already that we can use, but we're less interested in questions like how to implement a web server using this framework, right? And we're probably not interested in that so much, as much as we're interested to see how the effects are handled. What is so still, I don't think we have a good answer to the question of what happens to monad transformers that don't commute, right? So if you have effects handled in different order, is that somehow equivalent to having monad transformers applied in different order? Or is it not equivalent? Or maybe, so the latest intuition that I had from reading his comment, which I encourage you to read as well, I posted it, is that depending on the order in which you choose to handle the effects, then you will get results similar to what would be for a different order of monad transformers. I don't know how that can work, but I can also imagine So if you look at the coproduct construction, there's no notion of order of effects handling, right? So the coproduct construction is completely symmetric. You're supposed to supply all the handlers at once. So the coproduct is for all target monad, given the first handler, given the second handler, get the result, right? So you do not say that the first handler and the second handler are somehow asymmetric. They're completely symmetric.
They're not nested.
Huh?
They're not nested.
No, they're not nested, and there's no order. So it's right. So it's good. There's no.
So that the handlers you're talking about are the monad morphisms that go into the coproduct, right?
Right. Because these are the handlers, right? So you handle the effect and you get the result in the target monad. So
you're sort of injecting the effect into the target monad.
Yes, if you wish.
Not necessarily handling it, right?
Well, you handle it in the sense that you don't have that effect in your type anymore. So now the effect has been handled, and if you insist on purity, then no effect can ever be handled, right? So it must be absorbed into I/O. So that would be the Haskell way of dealing with it, right? So you never actually handle any effects in Haskell. You just absorb them into the I/O. The runtime handles them. And well, you can think about it in this way, but I see that in the coproduct construction, the handlers are these monad morphisms from each individual monad to the target monad. So the coproduct P plus Q is exactly the same as Q plus P, and there's no difference between them. There's no ordering of handling of effects. But in the Q KYO, it appears that there is an order of handling of effects.
So that would be a more conventional way of doing algebraic effects that we have looked at before in the other track. And I think my conclusion about algebraic effect handlers in general is that they are not necessarily monadic at all. There's a great deal of freedom in writing them, and what you get out of them may or may not be what you put into them is essentially the free monad, but what you get out of them may or may not be a monadic data structure at all.
Coming out of the handlers, like
Yes,
because you've sort of handled it, so you can kind of throw away some, or
well, you will often handle it by producing some sort of data structure that corresponded to your computation, and that data structure will often be monadic. And if you nest handlers, then you will often have some kind of composition of monadic something or others. And then comes the question of, well, what do you do with this composition? Maybe you need to think of it in terms of a monad transformer. So all of the stuff that we have talked about in terms of monads may still be relevant, but it also may not, because there's so much freedom in writing handlers.
So okay,
so about the coproduct stuff, I mean, if you weren't going into I/O, then it would seem like you would want to basically go into a monad stack. Like if you had exception and state, you would want to go into some sort of monadic thing that could handle both exception and state. And so you get back into monad transformers, and now order matters. Right.
Yes. Well, the coproduct construction has a quantifier for all m. Right? So it means that.
But you get to pick the
you get to pick it when you use that, right? So that's as an eliminator for this, and you can pick it. but before you pick it, it doesn't have any specific one picked. So the computation in the coproduct monad doesn't have any notion of how it will be run, in which order, and in which target monad it will be run. Now the thing is, that if you have specific monads P and Q, say, you require that the target monad M be such that there exist monad morphisms P to M and Q to M. Now, certainly for many monads M, they won't exist, and so there will be void types. And then it's you have arguments of void types. So it's void to whatever. So that will be completely useless. So you cannot use those monads to run this, and it doesn't matter. So that is just is completely harmless. So the fact that for most monads you cannot run into them is harmless from the type point of view. So this type is for all M, and then some of those for M are void to void, which is unit, which is fine. I don't care about it. It doesn't do anything. See what I mean? So it's a function from monad morphism to the target monad M, but there is no monad morphism for that target monad. So
but you want a target monad where there are morphisms.
Well, yeah, but this type itself doesn't fix the specific monad M.
Right.
And so for that, in some sense, this is for all monads M for which monad morphisms exist. And so this includes all monads M that are IO-like with arbitrary stuff that you don't know about. It includes all monad stacks that have enough power to represent all your effects. It includes the free monad built upon all your effects. It includes all of that. So you can run into any of those. You can run into a specific monad stack. You can run into a free monad. You can run into IO. You can run into all kinds of things. So you're free to do. So the type itself doesn't know that you're running into that. So the coproduct is completely symmetric. It does not know that you're going to run it into a specific effect. And your entire program is a computation in that coproduct before running, right? So your entire program, and so I'm trying to understand what happens with algebraic effects before you run them. So this entire program is a value of some type. What type can we pretend that we know what that type is? Right. So before you run that program, in the KYO or KYO, whatever, in the KYO, also you have some monadic value, or not monadic, I don't know, the program that is not yet run. Right? Apparently it does not yet have a fixed order of effects. It has these effects already denoted in there, but apparently you still have a freedom to apply handlers in different order. And I'd like to see. So anyway, so my real question is, so what's the plan for the next? So what are we supposed to do?
That's our question.
Right. Simplest thing is just read this getting started guide for Kyo. See if we can figure out what it does. Maybe write some code with it and experimentally see what it does.
Yeah.
Just basically, it's an excuse to give us another chance to think about how to implement effects.
Yeah. Okay.
So
sounds good to me.
So the other thing we would want to do is to think about what we would do for the following time.
Oh yeah.
Yeah.
That's a good question.
So
more homework.
Right. So the 5th of October, is that good for people?
Yeah.
I will actually be in
Are you
Athens.
still here?
I will be in Athens, but it will be a reasonable time of day. So
yeah, well, it's a good question of, okay, well, we can do that 5th of October, but it's a good question. Yeah.
I have a conflict, but please don't mind me.
Should we postpone and give a bit more time?
The Saturdays after that, I am like kind of booked. So, for me, then it would have to be the 26th of October.
Wow,
but
that is,
don't mind me.
that is rather like,
yeah, go ahead.
Yeah, Young Il, if you're okay with catching it on the recording.
Yeah, that's fine.
Okay, all right, let's do it on the 5th then.
All right.
All right.
And what shall we do then?
Well,
what shall we do after that?
After that, we will figure something out.
Okay.
Tim mentioned a book that is coming out based on Haskell, functional design and architecture. I don't know what.
Wow.
That might be far too practical for this group, but
design patterns, right?
The design patterns,
function-oriented design patterns.
Yes, basically, I think that is what the philosophy is. So.
He does have appendices on monads, though. So, yeah.
Okay, well, that is something.
Yeah.
Yes.
Because there are books now on functional programming that on purpose never say the word monad or functor or anything.
Right.
Yeah,
I got the impression he wasn't trying to dumb it down. It's more just like trying to fill in some gaps where people have not gone far enough in terms of showing how you could get things done in the real world. I guess it's a little like blasphemy, right? Though, because Haskell's whole thing was to not succeed.
Yeah, I know it's failing at not succeeding.
Yeah, well, I mean, to me, this is a bit weird. It's like saying an electronics engineer doesn't want to hear about the Fourier transform or about spectrum, because spectrum is such a weird word to say, right? And so the books about like radio and electronics, they try to avoid saying the word spectrum, and instead of spectrum, they say burritos or some other things. Right? Because spectrum or Fourier is just a horrible thing to say. Nobody knows how to spell that, and so or delta function or something like that, and nobody wants to talk about that, and so they have to say something about it, but they use different words because spectrum is just a horrible thing to say. No, it's just so scary.
Maybe that second link will make you happier, because that's trying to make category theory approachable to programmers.
Which one?
The Bartos.
Oh.
Yeah, we've already done that though.
Yeah.
Right.
Yeah. I was just joking that like that one's not. But
I see. Right.
The other one's not actually specifically avoiding monads, is it? Or like.
Right. The book isn't really out yet, so it is.
So where is this link again?
In the chat.
In the chat, yes. If you Google the book title, you will find the publisher's link, and I guess it's out on paper, but not out electronically yet.
Okay. Okay. Well,
yeah, sorry. The link is a Reddit link because the context of the other things that he said, and in particular, I was trying to share with the guys that the link to the voids of Haskell, where he touched on a bunch of interesting topics.
Okay.
And that's where the link to the Bartos
Yeah.
site came from.
Mm-hmm. Yeah, the Bartos book, we got through that some time ago in this group, and but the other one, okay, well, let me take a look at that. Maybe it's maybe it will be a book for reading.
I'd be interested in more Scala stuff, because that's kind of why I've been trying to figure out a way to make it to this track. Is that I like the idea of looking at functional programming through the lens of a language like Scala that is, in theory, capable of all of the functional goodness, but also quite practical in the sense that you deploying to a JVM is a fairly standard thing in the industry.
Yeah. Well, so next week's meeting should be good.
Yeah. Okay. Cool. Well, thank you guys.
All right. So thank
you.
Ciao.
And
Talk
see
to
you
you
in a
later.
couple of weeks.
All right.
Bye.
Have a good time in Athens.
Thank you.
Bye.
Bye.